Hello everyone, I hope you guys are all doing well. Today we are going to start to talk about logs and exponents. And before we start to get into the derivatives of logs and exponents, I want to do a little recap on what we know so far. And then we'll start towards the end of today's lesson to look at the limits of these types of functions. Okay, and when we're looking at logs and exponents, we really have to look at them hand in hand and look at them together, because basically they are two different versions of writing the same thing. Okay, so if we were to write something in exponential form, let's say we have x equals b to the y. Okay, well, just to go over some vocabulary, I know that this is stuff that you guys have been doing for a while. This whole thing over here, my pen just shut off, is called a power. And the power has a few parts. It's got a base. It's got an exponent. And it has a value. Okay, now we can write that in logarithmic form. This is written in exponential form. And written in logarithmic form, the equivalent expression would be log base b of x is equal to y. Okay, and so this guy is called a logarithm. And this guy is called the base of the logarithm. So the base of the logarithm is the same as the base of the exponent. This is called the exponent. And a logarithm is essentially equal to an exponent. And the value of the power is called the argument of the logarithm. Okay, and it's essentially what the power rather would be equal to. Okay, and these guys are basically two ways of saying the same thing. Now, why are logarithms used? Well, there's lots of reasons that logarithms are used. In science, they're often used to compare things that vary greatly. Okay, because remember, when we're just keeping track of an exponent on a number, now we are just keeping track of very, very, very large numbers versus very, very, very small numbers. So for example, if we're looking at the intensity of an earthquake, the Richter scale, that can track earthquakes with tiny intensities and very, very large intensities, because if we're looking at an earthquake with a Richter scale reading of 5, that's actually an intensity of 10 to the 5. The 5 is the exponent on 10, versus a Richter scale of 7, that's actually an intensity of 10 to the 7. So when you go up 1 point on the Richter scale, you're going up in terms of intensity by tenfold. And so logarithms are often used in science to compare things that vary greatly, so that instead of keeping track of the actual number itself, which could be tiny or enormous, we can just keep track of the exponent on the number. Okay, now we've been working with exponents for a really long time, and so hopefully we're pretty familiar with our exponent laws. And in fact, I've seen you guys use them a lot throughout the semester, so I know that you guys are familiar with those. And there's a lot of spin-offs on these laws, but there's basically 3 laws and then one sort of definition that we need to be aware of. The first one, and all of these can be proved through expansion. The first one is the product rule, or the product law, I should say. And that is when you multiply 2 powers, I'm going to switch back to black, with the same base, you can add their exponents. Okay, now in logarithmic form, remember that the logarithm itself is the exponent. Okay, so I would have something like this: log base a of b plus log base a of c Okay, well, think about it this way. This is sort of the value times the value. And this is exponent and exponent. I'm adding exponents, means I can multiply the values. So this is log base A of B times C. That would be sort of the logarithmic form of the product law. Okay. We also have the quotient law. So if I divide two powers with the same base, I can subtract their exponents. Okay, and so a similar type of law with logarithms, but instead of adding, we're going to subtract. Log base A of B minus log base A of C is equal to, written as a single logarithm, log base A of B over C. Okay, and then also there's the law of a power. When I take a power, whoops, I'm going to stick with x's as my base. There we go. X to the A, and I raise it to an exponent. Then I can multiply the two exponents together. Okay, so similarly, if I take a logarithm, remember a logarithm is an exponent, and I raise it to an exponent, then I can multiply the two exponents together. So the one exponent is C, the other exponent, because the logarithm is an exponent, is log base A of B. Okay, and finally, and this one is actually a definition, however, it fits in nicely with all of our other exponent laws, and that is that x to the 0, as long as x is not 0 itself, is equal to 1. Anything raised to the exponent 0 is equal to 1. And the equivalent logarithmic form of this is log base A of 1. We're essentially saying A raised to what exponent is equal to 1? Well, that exponent would be 0. Okay, so we've got all of these different laws in exponential form and in logarithmic form. But basically, they're just the same laws. One set of laws is written exponentially and the other set is written in logarithmic form. Okay, now in terms of their graph, I know I'm going to run out of room here. I'm going to have to move into my notes app. We looked at exponential graphs when we looked at limits. So let's look at y equals b to the x, and we're going to assume for this one that the base is greater than 1. So let's say, imagine that the base is 2. Okay, well, 2 to the 0 is equal to 1. 2 to the 1 is equal to 2. 2 to the 2 is equal to 4, right? So this is going to grow and grow and grow. 2 to the 3 is equal to 8, so it's going to get really big fast. And then if I go to the negatives, 2 to the negative 1 is equal to a half and then a quarter. So I get this horizontal asymptote going this way. Okay, now that's if b is greater than 1. If b is between 0 and 1, right? Let's say b is a half instead. It's the reciprocal of 2. Well, a half to the 0 is 1. A half to the 1 is a half. A half to the squared is a quarter, right? A half cubed is an eighth. So now we actually get a reflection in the y-axis when b is between 0 and 1, which kind of makes sense because every time x gets bigger, I'm having something. And every time x gets smaller going the other way, I'm doubling, right? As I go to the left, I'm doubling. So this graph over here is y equals b to the x, where b is between 0 and 1. Okay, now that is a graph of an exponential function. Now, before we look at the graph of a logarithmic function, what I want to bring to your attention is that graphs of exponential functions and logarithmic functions are inverses of one another. So let's say I wrote this to start. If I wrote the inverse function of y equals b to the x, remember inverse functions are when we switch x and y, I would have this, right? right? The inverse would be x equals b to the y. Now, if I wrote that in logarithmic form, okay, then I would have log with a base b, argument x, because the argument is the value of the power, is equal to y, or y equals log base b of x. Okay, so what does that tell us? It tells us that exponential functions and logarithmic functions are inverses of one another, and therefore when we graph them, we're actually reflecting in the line y equals x. We have just, all we've done is we've switched x and y. Okay, so let's suppose that b is greater than 1. For b greater than 1, well, that is going to correspond to the first graph I drew, right? So the y-intercept was 1. Now the x-intercept is going to be 1. Okay, the horizontal asymptote started to hug the negative x-axis. The vertical asymptote is going to hug the negative y-axis. And it's going to look like this. Okay, so that is if b is greater than 1. And then similarly for if b is between 0 and 1, then again, the y-intercept for the second graph I drew is also at 0. And this time the asymptote, instead of hugging the positive x-axis, it's going to hug the positive y-axis because I've essentially just switched x and y. So this is when b is between 0 and 1. And by the way, logarithms are only defined for, I should have mentioned this, positive bases and positive arguments, okay? Now, there was a couple other things that I wanted to talk about before we move on, but I ran out of space on this page, so I'm gonna actually open up my notes app and move over there. Here we go, let's start a new one. So another thing I wanted to talk about, and we're going to talk a lot more about this tomorrow, is the natural logarithm. And that is a log with base e. Okay, and that's equal to a special button on your calculator, and we actually use a special word for it, which is ln. Log base e is equal to ln. Now, e is a very special number. It's an irrational number that just sort of pops out of nowhere, kind of like pi pops out of nowhere. It's a bit of a mysterious natural number that comes about, irrational number, and it's equal to about 2.71. And we're going to talk a lot more about E tomorrow. So I don't want to go too much further into E right now. It has a ton of applications, I can tell you that. And it's used all the time, more frequently than you guys would even think about. Tons of applications all over the place. So we will talk more about that tomorrow. But if you see that pop up, that's what we're talking about. If you see ln b, you should assume it's a logarithm with base e. Okay. Now, last semester or last year, whenever you took 30-1, you would have looked at solving logarithmic equations. So for example, let's say I ask you to solve this. Ln of x plus 7 plus ln of x plus 3 equals ln of 77. Okay, so this is an equation that we want to solve for x. Now, the idea with solving logarithmic equations is that if we can have a single logarithm equal to a single logarithm, and the logarithms have the exact same base. And in this case, we do have the same base because the bases are all e, right? They're all ln, meaning the bases are all e. Then we can actually drop the logarithms and make the arguments equal to one another. Okay, that's only if we have a single logarithm equal to a single logarithm. We're not quite there yet, though. We have the sum of two logarithms equal to a single logarithm. So what we need to do is use our log laws to change the left side into a single logarithm. And we can use the product law here. If we are adding two logarithms with the same base, we can multiply their arguments together. So this is going to be the same as ln of x plus 7 times x plus 3, and that's equal to the ln of 77. Okay, now, if we have a single log equal to a single log, and again, the bases are the same, we can drop the logarithms and just say that the only way for this to be possible is if x plus 7 equals x plus 3. Or sorry, let me say that again. If x plus 7 times x plus 3 equals 77. I was thinking ahead and just talking without actually talking about what I was thinking about when I said that last line. X plus 7 times x plus 3 has to equal 77. Okay. Now we have a quadratic equation, and this we can deal with. Okay, so we're just going to expand. X times x is x squared, plus 3x plus 7x is plus 10x, and then 7 times 3 is plus 21, and that's equal to 77. Okay, so we can now equate to 0. And we're going to get x squared plus 10x, and then what is that, minus 56 equals 0. Okay, and so we're looking for two things that multiply to negative 56 and add to 10. And let's see, so 7 times 8 is 56. That 14 times 4, that will work. Positive 14 and negative 4. So x plus 14 times x minus 4 equals 0, which means that x equals negative 14 or 4. Okay, now you have to be careful because you could get an extraneous root here. Anytime you change the nature of an equation from the original type of equation to a new type of equation, there's a chance that you can get an extraneous root. And that's exactly what we did in this line over here when we dropped the logarithms. We changed from a logarithmic equation into a quadratic equation. And we did actually get an extraneous root, which is this one. It's the x equals negative 14, because you cannot take the logarithm of a negative number. So this guy is extraneous. Extraneous, oh boy. I think I spelled that wrong. Can't take log of a negative number. Okay, so the only answer here that works is x equals 4. All right, so that's how you would solve a logarithmic equation. Okay, so I think that's all the background that I want to do for now. Let's go back to our notes, and we're going to talk a little bit about the limits of these functions. Okay, so we're going to start to look at limits of these functions, and we'll start out with this one. Find the domain of f of x equals ln 9 minus x squared and evaluate the limit as x approaches 3 from the left of f of x. Okay, well, let's start with the domain. Here, we're taking the ln of, there we go, the ln of 9 minus x squared. Well, we can only take the logarithm of positive values. So that's where we're going to get our domain from. 9 minus x squared must be greater than or equal to 0. Okay, well, to figure that out, we have to factor this. That's one way of doing it. We could make an interval table, right? These are going to be the zeros. The zeros will be at x equals 3 and negative 3, by the way. So, you know, negative infinity to negative 3, negative 3 to 3 rather, and then 3 to infinity. And then we're looking at each factor, 3 minus x, 3 plus x, and then what's the sign of the entire expression? Because we want that to be greater than or equal to 0. Sorry, 9 minus x squared. There we go. Okay, so when x is negative, let's say x is negative 4. 3 minus negative 4 is positive. Okay, let's say x is negative 4. 3 plus negative 4 is negative. Okay, between negative 3 and 0, 3 minus 0 is positive. 3 plus 0 is positive. And then between 3 and infinity, let's say x is 4. 3 minus 4 is negative 1, so that's negative. 3 plus 4 is 7, so that's positive. Okay, so if we're multiplying the two together, this will be negative, positive, negative. So this is our domain. Okay, so, and because it actually has to be greater than or equal to 0, we can include the end values as well. Okay, so the domain is from negative 3 to 3. All right, now, in terms of this limit, okay, well, if I'm approaching 3 from the left, and by the way, I can't approach from the right because that would be outside of the domain, then essentially what I'm doing is I'm going 9 minus almost 3 squared. Okay, 9 minus almost 3 squared is almost 0. Right? It's a very small positive number. So this is going to be the limit as x approaches 3 from the left of a very small positive number. Okay, now you have to think to yourself, if I were to convert this back into exponential form, right? 3 raised to what exponent equals almost 0? And you have to think in terms of the exponential function. Think about 3 to the x, okay? If I think about 3 to the x, and I want to know what's the y value, what's x when y is almost 0? Well, that's along the horizontal asymptote, right? That looks like this. When y is almost 0, right, x is approaching negative infinity. So this limit is negative infinity, because when y is almost 0, that's when it's starting to hug that horizontal asymptote. When it hugs the horizontal asymptote, x is approaching negative infinity. So this limit is negative infinity. Okay, so when you're working with logs and exponents, you're almost constantly thinking back and forth between the two versions, exponential version and logarithmic version. Okay, this would be like y equals 3 to the x. Okay. All right, now in terms of these other limits, well, exponential limits, we actually looked at this a little bit when we were looking at sequences and series. So if I'm thinking about what's the limit as x approaches infinity of 6 to the x, well, that graph looks like this because 6 is greater than 1. That looks like that. So as x approaches infinity, y also approaches infinity. So this is also infinity. Okay, now the limit as x approaches infinity of 3/4 to the power x, well, the base here is less than 1. So this would look like that, right? So as x gets larger, y gets smaller and starts to hug the x-axis, and the x-axis has a y value of 0. So this limit is 0. Okay, this limit, the limit as x approaches infinity of 7 to the negative x, well, this is the same as the limit as x approaches infinity of 1 over 7 to the x, right? You always want to think in terms of a positive exponent. And again, now the base is less than 1, between 0 and 1. So this limit will also be 0. Okay, and then we have the next one is the limit as x approaches infinity of 5 to the 1 over x. Well, that's like the limit, or actually that's like 5 to the 1 over infinity. Well, 1 divided by infinity is essentially 0, which is 5 to the 0. And 5 to the 0 is equal to 1. Okay, now this guy, the limit as x approaches 1 from the right of 0.9 to the power 1 over x minus 1. Well, if I'm approaching 1 from the right, then I'm a little bit above 1. So x minus 1 is going to be positive because I'm a little bit above 1 minus 1. So this will be 0.9 to the power of 1 over a little bit above 1 minus 1 is a very small positive number. Okay, now 1 over a very small positive number is 0.9 to the power, well, essentially 0 again. Sorry, I apologize. 1 divided by a very small positive number. 1 divided by a small number is infinity. My bad, right? 0.9 to the infinity. If you multiply a base that's less than 1 more and more and more times, you're going to get 0. Okay, so these are the various limits. Next class, we're going to start to look at the derivatives of some of these functions, and I will see you guys then.